Welcome to this edition of Models 2 ACE. Presenting an Excel spreadsheet-based model to derive a set of hubs connecting all nodes for the hub and spoke route model of an airline system. Using linear programming, an airways company needs to design a hub and spoke system along its route for optimizing routes and flight costs, while providing the best connectivity to its passengers. There are 6 nodes, labeled A, B, C, E, F and G. These form a cluster of nodes. Though there exist direct routes between each pair, it would be prohibitive to dedicate flights for each pair of routes. So, these 6 nodes get connected to a hub, labeled Hub 1. This hub is used for connecting flights to and from nodes within a threshold of 1,000 miles of the hub. This restriction is made from the point of view of reducing a passenger's time on flight. Hub 1 could then be joined with another such hub, labeled Hub 2, that has 4 other nodes, labeled I, J, K and L within its ambit. This Hub 2 is used for connecting flights to and from nodes within a threshold of 1,000 miles of the hub. Let us examine the spreadsheet model, in this tab titled Network Details. This matrix, named Route Lengths, represents the routes between nodes served by the airlines and the distance by aerial route between the corresponding pair of nodes. For example, this value of 1,700 in cell D3 indicates that a direct flight route between nodes A and B would be 1,700 miles long. The company desires to derive the smallest number of hubs that cover all nodes. We construct this table candidate for hub, of binary values, detailing possible nodes that could be made hubs, between every possible pair of nodes, based on the criteria that any node must be within a threshold of 1,000 miles of the hub. For example, since nodes A and B are 1,700 miles apart, B cannot serve as a hub for A, and vice versa. This fact is indicated by this value of 0 in cell D19 and correspondingly, in cell D20. Conversely, this value of 1 in cell E19 indicates that node C can serve as a hub for node A, since they are less than 1,000 miles apart. Let us clear out the values from all the cells in this binary matrix, except the first cell D19. Observe this if condition, set in the value of cell D19. If the corresponding value in the route lengths table, in cell C3, is less than the threshold of 1,000 miles, B can serve as a node for A. Dragging this across all other cells in the same row, we replicate the formula to those cells. Next, selecting all cells along the first row and then dragging them across the remaining rows, we replicate the formula across all the rows. This binary matrix, along row 33, named Array Hub, indicates whether the corresponding node is selected as a hub or not. For example, this value of 0 in cell C33 indicates that node A is not selected to be a node in the network. This value of 1 in cell D33 indicates that node B is selected to be a node in the network. This set of values in these cells would be derived by the model, using linear programming. Hence, they represent a set of decision variables, and are shaded in green. The sum of these 1s and 0s is captured in this cell R33, named Total Hubs. This sum is to be minimized. These set of values in column P denote whether each node along the rows, in this table, is covered by a hub or not and contains the number of hubs covering the node. For example, for node F, both the selected hubs, B and C, are connected to it, being within the threshold of 1,000 miles. Hence, this value of 2 under the column named Covered by Number Hubs indicates that node F is covered by 2 hubs. This value can be elegantly obtained by performing a sum product operation between this binary vector corresponding to the feasible nodes for node F and this binary vector denoting the hubs that are finally selected to be nodes. Obviously, since every node must be covered by at least one hub, we have this set of lower bound constraints of 1s along column R, under this label number min hub coverage. Each of these values in the array covered by number hubs must be at least equal to 1. Denoted by these constraint operators and set of 1s. Let us clear the decision variables along this binary matrix array hub. Launching Solver, we verify the functional constraints under the Constraints section. This constraint stipulates that the values of the numbers in array hub must be binary integers. The objective function is set to this value of total hubs, which is set to be minimized. Under solver options, we check the box next to ignore integer constraints and select the option to make unconstrained variables non-negative and select the simplex LP method for deriving the solution. We now instruct solver to derive the optimum solution. Solver reports that it has found a solution, where all constraints and optimality conditions are satisfied. This is the set of decision values that solver has generated. The solution suggests that only nodes B and C are enough to be made nodes to serve the entire network. Every node in the network is served by at least one node, as can be verified by these values along the column covered. Summarizing the optimal configuration of nodes produced by the model, the decision variables, contained in the cells shaded in green, were the decisions on whether a particular node was to be made into a hub or not. The consequences of the decisions on the hubs were the number of hubs serving each node and the number of hops a passenger would have to make between a source and a destination. In addition to the functional constraint that the decision array was to be a binary array, the constraint condition of the problem was that each node must be served by at least one hub. The objective function minimized the total number of nodes in the network. Thank you for giving Models to ACE the opportunity to serve you with our analytical models. Please subscribe to our channel for more.